Hello, everybody, and welcome to another wonderful day of kinetics. So today we're going to focus in on that ever-important topic, reversible reactions. So when we're talking about reversible reactions, really what we're meaning is any sort of reaction where I can have a reactant that transforms to a product, and then it can go back and forth. And so you can imagine this occurring with just uh, a single species like A and B, or with, say, A plus B goes to C, or any other permutation. However, we want to really kind of focus in on this idea of reversibility when just focusing in on this simplest of cases. So if I'm going to try and examine the kinetics for this system, the first thing I'm going to want to start with is the idea of the rates of reaction. So I can examine the rate of consumption of A of formation and consumption of A. And so when I start with this idea, I have one reaction that's going to consume A, and this is going to be our forward reaction, which is going to proceed with a rate constant of Kr. And because this is an elementary reaction, it is going to be first order in A. So again, concentration of A will be decreasing with this reaction. But I also have this reverse reaction, which is going to produce some quantity of A. And it's going to proceed with a rate of Kr prime. So this is the rate constant for the reverse reaction. And again, first order in B. Now, this one gets a little bit messy with trying to figure out how the concentration of A is going to change, because now I have this pesky issue that I am first order in A and in B. So this gets a little bit messy. So when in doubt, our solution is to always put all of our concentrations in terms of one single species. So in this case, I can essentially substitute out the behavior of B, or the concentration of B, in terms of the concentration of A. And here we're using essentially the reaction itself, that for every mole of B produced, I've essentially consumed a mole of A. So simply by looking at my starting amount of A and my ending quantity of A, I can figure out moles of A consumed, which gives me moles of B produced. Then what we can do here is substitute in our expression for the concentration of B into our rate equation, and we get something that gets a little bit fun, because now I have the concentration of A in terms of the change in the concentration of A in terms of the concentration of A and my initial starting concentration of A. And well, let's be honest, this is a little bit messy. So we're going to want to rearrange the equation a little bit. First good place to do this is going to be trying to combine all of our terms that involve the concentration of our reactant. So in order to do this, we're going to want to first distribute this term with Kr prime, so the rate constant of the reverse reaction. And then when we do this, it's fairly easy to see how we can then combine the terms that involve the concentration of our reactant, because they will both have a precursor of negative, one has a precursor of negative Kr and one of negative Kr prime. So I can essentially treat a unified coefficient of negative Kr plus Kr prime. And then again, leaving behind a term just in terms of the initial concentration of A. So this actually gets us our general rate equation for the change of A. However, as we've seen before, what I really care about are integrated rate laws, as they'll tell me what the concentration of the system looks like at any given point in time. Well, it turns out that this is a nice, simple exercise in differential equations, which I'm sure that not many people want to do right now. However, we can go ahead and determine the pre-salt integration form to give us a concentration of A solely in terms of the initial concentration of A. And again, with respect to time. In this case, time is going to show up in the as an exponential term. So using this new integrated rate law, I can figure out the concentration of A at any point in the reaction trajectory. So this is actually a very useful feature for me to make use of. But in general, we're not that interested at any given time point. We're often interested in several very select time points. Most common being initial and final conditions if I let the system go to equilibrium, and occasionally we're often interested in half-lives. But here we're going to want to focus in on two major features. First, we want to make sure that the initial conditions produces a logical answer. So we can go ahead and plug in a value of t equals 0. And when we do this, we'll note that this whole exponential term goes to 1. And so all I'm left with is the reverse rate constant plus the rate constant over the rate constant plus the reverse rate constant. So this whole expression goes down to 1. And we do indeed confirm what we would originally expect, which is the concentration of A at time 0 is the concentration of A at time 0. So we do actually pop out a logical response. However, we also want to verify a more interesting time point, which is long times. So if I let this reaction sit out forever, this gives me essentially a time infinity. So for some reactions, this will be achieved by letting it sit out for, say, 10 hours if it's a fast reaction, or 10 million years if it's a long reaction. But in general, we can see what happens if I look at this infinity time period. So when I do this, what we'll note is that this, as my time goes to infinity, I have exponential of a negative expression, which essentially brings this whole term close to 0. And so all I'm left with is the rate constant of the reverse reaction over the rate constant for R, the rate constant for the forward reaction plus the rate constant for the reverse reaction. So this actually shows me a very kind of cool feature, that if I have a very fast rate for the reverse reaction, so a large rate constant, this means that I would expect to have a concentration for A that's very similar to my initial rate constant as my initial concentration, as the rate for the forward reaction would be relatively small, and the expression then becomes dominated by the reverse rate constant over itself. So again, we see very little reaction. And this should make logical sense because if I have a slow forward rate and a fast backward rate, I'm essentially trying to swim up current. It's not going to work very well. Contrarily, if I have a relatively small reverse rate and a fast forward rate, well, then what happens here is that my reverse rate is going to be relatively small, and the system's is going to quickly become dominated by the forward rate constant. And so I should expect my system to become quickly depleted, which again is exactly what we would expect. However, we're not just interested in the concentration of a reactant. One might even say that we're far more interested in the concentration of our product. And again, we can get the concentration of our product by looking at the initial concentration minus the current concentration of A. Because again, the amount of A consumed gives me the amount of B formed. So I can essentially subtract my current expression for A from my initial concentration. However, here we run into the wonderfulness that is denominators. So in order to actually make this difference equation work, I need to make sure they share a common denominator. So I'm just going to express my initial concentration in terms of 1 as the denominator over the shared denominator over itself. So when I do this, what you'll notice is that I'd be subtracting the forward rate constant plus, so I'll take the forward rate constant plus the reverse rate constant minus the reverse rate constant, which, go figure, gives me the forward rate constant over the sum of the two rate constants. So again, we can apply these same sort of limiting conditions. If I have a large forward rate, what we end up having is that in the denominator, The forward rate is going to control the system, and then I end up with the forward rate over itself. So this whole expression will quickly start to approach 1. And as it approaches 1, what that then tells me is exactly what I would expect. All of my initial A has now formed the product. So I have a complete reaction. So again, this should hopefully make sense, because if I have very little reverse reaction taking place, the reaction quickly goes to completion and all of A becomes B. Contrarily, if I have a small forward reaction and a large reverse reaction, I'm going to see very little B formed. Again, just like we saw when examining the concentration of the reactant. And this kind of helps set some limiting conditions that we can examine the system and will help us predict what happens as our reaction proceeds. Because again, as our reaction proceeds, we should see a decrease in the amount of A and an increase in the amount of B. Where with again, the exact amounts of A and B will be predicted by the relative values of the forward and positive rate constant. So in this case, where I see more product formed than reactant consumed, this tells me that the forward rate constant is larger than the reverse rate constant. And as you would play with these two, the ratio of these two values, it's going to change the ratio of where my infinite time concentrations will end up. However, we do actually have a pre-built expression that is good at describing the concentrations of two species after long periods of time. That's our equilibrium constant. Because after long times, it would be safe to call our concentrations of A and B as being at equilibrium. So thus my K, or my equilibrium constant, will just be the ratio of these two species. And you'll note that they all share a dependence on the initial concentration and a shared denominator, which quickly reduces the system to the equilibrium constant simply being the forward rate divided by the backwards rate. And this should also help give us should hopefully make sense, because this is how we originally define equilibrium systems, or even reversible systems early on, is when I have equal pressure moving in the forwards as in the backwards direction. So this hopefully kind of brings an idea of what we were talking about when we're talking about reversible systems. And again, I do want to make note that there is certain circumstances when we build in extra reactions supporting this simplified system, where you can have a system where the forward and backward rates do cancel out, but the system's not at true equilibrium, because I haven't given enough time for, say, a following reaction to essentially slowly deplete the system of B. So again, this gives us a more version of a steady state version of the system. However, next time we're going to focus a little bit more on what these forward and reverse reactions look like from a thermodynamic perspective, as we go for one last combinations of how thermodynamics and kinetics really kind of help overlap. So next time, it's time for transition state theory and the Arrhenius equation. Until then, take care.